Hello students, in this lecture we will calculate energy density of the electric field in continuous charge distribution. In the previous lecture we have found the energy of continuous charge distribution. Energy density means energy divided by volume. So that is what we want to calculate now here. This was what was derived in the previous lecture, that energy of the continuous charge distribution half volume integral of phi rho dV plus half surface integral of phi sigma ds. It is the equation 1. Then we have defined something called as the electric displacement vector D, and that was defined in the Gauss's law in the dielectric. In the same chapter, we had shown that volume charge density rho is del dot D and surface charge density sigma is vector D dot n cap. So n is this unit vector perpendicular to the conducting surface. Now here what happens is this volume is there for this dielectric region of that continuous charge dielectric region, and this sigma is there for the conducting surfaces. Now substitute this in the equation 1, we get this equation 2. So we have substituted here rho equal to del dot D and sigma equal to D dot n cap. Now we have to simplify this, because here what happened, volume is there, here surface is there. So surface we have to convert into the volume, so that we can take the energy divided by volume to get the energy density. Let us consider this del dot phi d. So phi is the one function, it is a scalar function, d is another function which is a vector function, and del ordinarily it means it is a derivative. So derivative of the product, u v dash is u v dash plus u dash v. So derivative del dot phi d is the first function phi, derivative of the second function, but here dot is there because both are vector quantities. Del is a vector quantity and d is also a vector quantity here, plus derivative of the first function, it is a grad phi, because phi is a scalar function, so we cannot write that dot or cross in between. Then this quantity is vector, so into the second function which is vector d, so you have to write here dot product, because this is vector quantity and this is a vector quantity. Then next we find phi del dot d. So we take this on other side, that phi del dot d equal to this term del dot phi d minus this term grad phi dot d. Now this we have found in order to substitute this in this equation 2, in the first integrand of the first term. Okay, this was that equation 2 on the previous slide, and this is what we found in the previous slide. So substitute this in the first term, integrand of the first term. So when you substitute, you get like this. So this phi del dot is substituted there and the dv is there. Second term continues as it is. Then distribute this integral over these two terms. So there is open the bracket. So half integral of del dot phi d dv minus half integral of del phi dot d dv, plus that this second term here, it becomes here a third term. Next, use a divergence theorem in the first term and substitute E equal to minus grad phi in the second term. So here when you use a divergence theorem, volume integral of divergence of the function here is phi d. See, volume integral of divergence of the function is equal to surface integral of that function phi d, and since it's surface integral, this ds is there, and we write here n cap. We'll come to that why that dash is written little later. Then minus grad phi is vector A, so this sign becomes plus, and this third term continues as it is. Now here S is area of all conductor in the system. See, we had said that volume charge distribution is there, so it is also the surface area. Then conductors are there, so conductors also have the surface. Now these conductors are inside that charge distribution. Then S dash area which bound the system of conductor from outside. So that's what in fact we had considered in that third chapter. So S plus S dash is the area of the entire surface bounding the volume B. So that area which bound that entire volume, and this S is a surface area of those conductors which are there inside the charge distribution. So now here that S plus S dash, so we separate this integral. So S and another integral for S dash, and this second and third term in the previous slide become this third and fourth term. So here integral over S plus S dash. So we have written separate integral for S and separate integral for S dash. Then this n dash equal to minus n, because see that surface S dash, it is surface covering that charge distribution. So it is for a closed surface, the direction of the area vector is perpendicular out. So direction of that n dash is directed out of the volume. But those conductors are inside the outer surface. So inside this. So now these surface are covering the conductor. So again the direction is out of this conductor, but it is into the volume of the charge distribution. So that's why what happens is the direction is opposite. So n dash equal to minus n. Then here substitute that n dash is minus n, and remaining term you write as it is. Then this this half integral S phi d dot n plus this phi d dot n dash ds, and this here it is there phi d dot n ds. So this term, last term and first term cancels. This term and this term cancel because this is a minus sign, this plus sign. What remains are these two terms. So here that is what they remain. Then S dash is moved out to the infinity. Then if it is taken to infinity, then potential is 0. They are not there in the system. So phi equal to 0. So what remains is only this term. So half integral, volume integral d dot e dv. If the field is uniform, then this will remain same at each and every point. D dot E will remain same at each and every point in the volume. So it will come out of the integral. So it is a constant. It comes out of the volume. This is what we have found in the previous slide. And this from the earlier chapter, D equal to epsilon E. So let us calculate energy density. Energy density is energy divided by volume. So here energy divided by volume, or we get is half d dot E. If the system is isotropic, same direction, then all physical quantities have the same direction. So d dot E equal to d cos 0. Cos 0 is 1. Then from this equation E equal to d by epsilon. When you substitute, you get here half d square by epsilon. This is one expression for the energy density, half d square by epsilon. Then if you put d equal to epsilon E, and that epsilon will, one epsilon will cancel or give half epsilon E square. So this is another expression. And we also know that epsilon equal to k epsilon 0. So therefore energy density is half epsilon E square is also equal to half d square by epsilon. This is an expression for energy density.